Great. Okay, so we should be recording now. I'm going to share my screen. And can everybody see Quantum Algorithms for Beginners, Lecture 3?
Yes.
Okay, so just to kind of refresh, Jackie, when we left off last time, we finally introduced notions of, we looked at what a quantum bit of information looks like, and we chopped up this block sphere, and we talked about, there's portions of it that are represent states that are in superposition. So that's that Schrodinger's cat state where you're not sure whether you'll get a 1 or a 0. And if you're closer to the North Pole on this ring, that means the 0 outcome is more likely. If you're closer to the South Pole, it means the 1 outcome is more likely. We talked about how if you allow yourself to be in superposition here on the equator, all of these states are equal distance from 0 and 1. So that means you still have, all of them have equal probability of seeing a 1 or a 0, but yet they are distinct states. And what makes them distinct is this new concept of phase, which we haven't talked too much about why it's important. But it can be it is a useful feature of quantum computers. And the hand wavy argument that you might hear is that quantum computers use these phases. Think of waves when they're in or out of phase, like a noise canceling headphones job. A wave comes in and it generates a wave in the opposite phase. So that would be 180 degrees rotation to cancel the incoming wave so you don't hear any sound. A quantum computer, in a similar way, choreographs that interference between quantum states of different phase to try and produce a solution that has probability of being measured and spitting out the quote-unquote solution to the problem. That's a hand-wavy answer. It's not really the whole picture, but that's just one way you can think of it going forward. And we left with this kind of thought experiment of how do you make entanglement? And we talked about how you can't actually make entanglement unless you have more than one qubit. And so we returned to this experiment that we had done where we were previously running these bits and sending them through an XOR gate or a controlled NOT, where we remember if the top qubit is a 0, you apply the bit flip gate to the bottom register. Or excuse me, if the top bit is 0, you do not apply it. If it's 1, you do. And so the question is, well, that's all fine and dandy if you've got classical bits in the top qubit, but what if that's a superposition? What if you what if you apply a gate based on whatever state Schrodinger's cat happens to be in? What happens then? Um, and so this is how we kind of want to motivate the value of performing measurements, because we need the language of measurements in order to talk about what happens with this setup. This setup generates the famous Bell pair. These are the canonical example of an entangled pair of qubits. So what ends up happening at the end of this is that you want to think of, well, so you're in this you're in this state of quantum uncertainty. The top qubit was uncertain as to whether it was a 1 or a 0. And because of that, it kind of spread its uncertainty to the bottom register. So now that bottom qubit, well, I don't know what state it's in. It might be 0 or it might be 1. And because of the quantum nature of these things, we actually can think of, we can now think of these two states as being connected. If I look at the top qubit and I see a 0, then the bottom qubit will be a 0. But if I look at the top qubit and I see a 1, then the bottom qubit will be 1. The rough way to think about it that I like to use is quantum doesn't break the laws of logic. Like, you're not going to see a quantum state measured in one place that disagrees with what would have happened in another place. Like, the agreement has to be there even if there's still uncertainty after the circuit has been run, which is maybe a little convoluted. But the bottom line is we need measurements to talk about, what this Bell pair looks like. And so that's how I'm trying to motivate this third lecture here. So we started with this last time. We talked about, what does a quantum computer do? If you're sending a job to a physical quantum device, that would be on the left-hand side. It would start off, it would prepare a quantum system, an array of quantum bits. It would start them off in some starting state. Usually, quantum algorithm people assume the starting state is everything is in the zero state, but that doesn't have to be the case. Then the algorithm side is you apply a bunch of gates. We've talked about the rotation gates, the X, Y, and Z rotations about various angles. And we've talked about the control not gate that is helpful, as we've just seen, for generating entanglements. Today we're going to focus on, so we've talked a little bit about those gates, and I haven't told you too much about like useful circuits you can run with them yet. But today we're going to focus on how at the end of the process you can extract classical information from that whole system. Because the quantum computer can exist in states that we classically can't see. Like you can't physically see a Schrodinger's cat both alive and dead at the same time. You can only see it as one or the other. So you can think of a quantum computer as being able to store information in this special quantum state, but you can only extract from that classical information. You can never actually physically see the quantumness. The quantumness ends up realizing itself in the classical information that you read out of the device. So that's what I mean by a measurement. You measure those qubits, you measure those Schrodinger's cats, and you see some configuration of ones or zeros. And we want at the end of the day, the computer to store the answer to a useful question into the value of those measurements. And we want to talk about how that happens today. So we've talked a little bit about like there's something special that goes on in the quantum realm. And the question is like where do things start acting like quantum objects? You've got cars, which I think nobody is going to assume your car can behave quantum mechanically, but the question might start to get blurry. Do you see quantum behavior at the level of proteins? Maybe more likely you see it at the level of molecules. I think probably certainly we see it at the level of atoms. And by the way, on the bottom right, that picture is supposed to be a nice, more realistic representation of an atom than like the little solar system model you typically see. That representation tries to capture the quantumness. It's a YouTube video I'm quite fond of. But Jackie, this is a question for you. Where do you think we might need to pay attention to quantum effects? Do we pay attention at the level of one of these four? Like how big can you get and still see quantum?
I think probably as big as macro objects.
And explain why.
Mm. Just because quantum can be so like I'm trying to find a way to say it. Well, there's so much that goes into like quantum that I feel like it could be in objects as big as like cars. We can probably see like some quantum algorithms or behaviors and things like that.
Yeah, so I mean, I think, and I've been working on a lecture to talk about this, but have you ever been in an MRI machine?
No.
Do you know what they are? They're like these
Yeah.
big donut-shaped things. They can image soft tissue. Those use quantum properties to visualize macroscopic tissues in the human body. Typically, people don't think of large-scale objects like cars as behaving quantumly. But you're right that these objects are made of quantum pieces. So, in the case of humans, we've got all these molecules inside of us, like in the bottom left corner, all these atoms, and those atoms are made of, even smaller particles. The MRI machine can register the magnetic field generated by, say, the nucleus of an atom inside of your body, and that will be affected by the other atoms in the molecule that it's part of. And that's how MRI machines identify the different types of tissue. But for our purposes, I think, in the space of quantum chemistry, I think the largest we can go where quantum effects may be realized is on the scale of proteins, for at least for this exercise. But it's a philosophical question that actually is currently an open field of discussion where physicists, I think, don't have haven't come to a full consensus on, where the precise boundary between the quantum and classical world falls and why it might fall there rather than somewhere else. That's kind of a philosophy of quantum question. But for now, we can think of atoms are certainly quantum, molecules absolutely, proteins still yes, but starting to get large. By the time you get to the size of a cell, it's controversial. Some people are trying to do research about whether cells interact via quantum effects. I know someone who's doing that at UCLA. But that's kind of getting for a little bit further towards the fringe. So certainly proteins, molecules, and atoms, we can talk about quantum effects. So for now, let's just focus on things that are smaller than atoms. So the electrons, protons, and neutrons that make up an atom. And we're talking today about measurements. So the question is, I've got this depiction of an electron on the left. And real quick, just want to clarify that when we imagine particles as little balls, like this artistic representation is showing, that's really not what these things are. If you have an electron bound to an atom, these are more accurate depictions of what that electron's wave function might look like. So just keep in mind as we're going through this that the left-hand picture, it might be useful, but it isn't accurate. So we want to talk about how do you extract, what sorts of measurements can you perform on an electron? What kinds of information can you pull from that? And we're imagining now our quantum computer. We want to build it out of electrons. Electrons are now the qubits that we're going to be using. And so the question is, what properties of the electron give you the sort of 2, 0, and 1, kind of poles of that Bloch sphere that an electron uses? So there's various properties we could measure about an electron. We could ask, where is the electron? We could measure its position. We could ask how fast and in what direction is it moving. We could talk about momentum. We could ask, especially if it's bound to an atom, what is the energy of the electron? How much energy does it have? We could ask, what is the mass of the electron? What's the electric charge? What's the magnetic spin? And can you tell me, which of these are all the various properties. We want to pick the one that can only give us 2 discrete answers. We might not know which one, but it can only give us 2 numerical answers because that'll give us our qubits that we're looking for. So first I'll ask mass and electric charge. Does that give us 2 discrete answers? No. Electrons have the same mass. They all have the same electric charge. This is actually a feature that you use to identify, oh, that thing's an electron because it has that mass and electric charge. So because those things are constant, if you measure them, you're not going to get probabilistic, ones or zeros. You're not going to get a distribution of answers. So maybe we want to look at position or momentum. Those things are quantum. You can describe them using a quantum state. Let's say you have an electron trapped in a box that's 1 meter wide. It'll be somewhere in there from 0 to 1 meters. So that is a quantum thing you can measure, but the challenge there is that variable is a continuous one. It could be at 0.5 or 0.51 or 0.53 or 0.0123456, right? It could be at any point inside of this box we've created for the electron. And continuous quantum variables is a whole field unto itself, but for our purposes, it's not what we want to be using. You could measure the energy of an electron, and again, I'm imagining this electron might be bound to an atom. So you will have a discrete energy. It will be quantum, so in the sense that you'll not be able to tell a priori what it'll be beforehand, but it can be more than one value. So an atom can have an electron bound to it, and that electron might sit at the first energy level, the ground state, the lowest energy. It could be 1 level higher or 1 level higher, or it could be, a number of energy levels higher up. So if we only want 2, some people rig up their experiments to try and restrict the electron from going higher than 1 energy level. And if you do that, then you only have two, there's a qubit. But for our purposes, I like to think of the spin, the magnetic spin of an electron. And so what you might ask, what is this property and why do we call it spin? It's kind of mysterious, but for the purposes of time today, you can just think an electron. We already talked about the fact that it has an electric charge. It gives off an electric field. And similarly, an electron has a property called magnetic spin, which means that it gives off a magnetic field. It interacts with magnetic fields. And so when you measure the spin of an electron, you're measuring which direction that spin is. And so you could measure it as up, that would be your 0, the top of the Bloch sphere, or down. That could be the 1, the bottom of the Bloch sphere. And I picked electron spin. People build quantum computers using qubits of all sorts of different, ways. Electrons might be one way. But I like this way because it feels more directly analogous to the visualization we've been using of the Bloch sphere. So you can imagine this Bloch sphere as the representation of the different directions that you could measure the magnetic field. You could measure in the z direction, which is that vertical axis on the Bloch sphere that you can see there on the screen on the right. You could measure it in the x direction or the y direction. And so those measurements of magnetic field can be represented using what we call the Pauli operators. And these are just special cases of these rotations we already introduced. So because they're so special, they get their own name. So instead of writing r sub z of pi, which is a 180-degree rotation about the z axis, I'm just going to denote that as the Pauli z. And so again, we're talking about measurements in this section. These you can think of as measurements of magnetic spin of an electron. So that blue vertical line is a measurement of the z-axis. And on the bottom left corner, you can see how you would represent that in a quantum algorithm or in a quantum circuit. Okay, I'm going to move a little bit farther forward and happy to answer questions, but I just want to make sure I leave enough time for Victory's his section. So for now, you can think of just there's these 3 different measurements that we can perform, which are related to these Pauli gates, these Pauli operators, and we can represent them as with these little the box with the little swoop and the cross. It's meant to look like the dial on an instrument, like it's a voltmeter or something like that. That's where that notation comes from. So it's basically just diagrammatically representing, oh, I'm measuring the magnetism in the z direction, or measuring it in the y or the x. And just a little note on notation, because the z magnetic measurement aligns with the 0 and the 1, those standard basis elements, we typically just don't leave the z off. So if you see a box with a dial in it that doesn't have an x, y, or a z, it's assumed that it's a z, because that's the most common measurement that people use as the kind of the standard one. Okay, so again, we talked about like these measurements, they physically mean, how we're extracting information from the circuit, how we get a 0 or a 1. That could be the Schrodinger's cat, finding it alive or dead. And those measurement outcomes are what comes out of the circuit. So let's see. So the measurement can be thought of as a question. You're asking the electron, is your spin up or down? And it could be quantum, it could be uncertain, and then that uncertainty could be this, a blue dot that isn't exactly on that vertical z axis. And so if you describe it as a sum, what this sum does is it basically just tells you the likelihood of each 0 or 1. Remember how we said if it's closer to 0, it'll be more likely to be measured as 0. And so this is just our way of now quantifying what is the probability of measuring 0. Well, it's the coefficient in front of it squared. So if there was a square root of 1/2 in front of that, I square it, then the probability is a half. That would be on the equator. I'm going a little fast, so we can. I'm happy to answer questions on this, but the bottom line is you can measure this thing, and if it's in a quantum state, it'll give you a probability of 0 or a probability of 1. And you can do that with many, many qubits. You build a quantum computer to have multiple components, not just one. So that's happening, for each of those. This is the point that I wanted to get to at the end here. So we talked about how what a quantum computer does. We can focus here on, a quantum computer can be thought of as a device that encodes the solution of a problem into the measurement outcome of its qubits. So you can just think of the measurement as the finale, the end result that actually tells you what you wanted to know about the solution to your problem. And so the question is, how does a quantum computer encode the results of a computation? It might do it in a couple of different ways. But the first one, like let's say a silly problem, you're asking the quantum computer to tell you where to eat for dinner, and you've encoded a bunch of different answers. The quantum computer computes all these crazy things, figures out the absolute best restaurant for you to eat at, and it spits out just a single bit string. And that bit string corresponds to a specific restaurant that you've encoded. So that could be one way a quantum computer tells you the answer. It just tells you one bit string with 100% probability, and all the other probabilities of the other bit strings are 0. More commonly, I see a type 2 answer where instead, let's say you want the quantum computer to calculate 5 plus 3. That's 8. The quantum computer could encode that answer with by giving a specific bit string 0.8 probability of being measured. So you can think of the quantum computer can encode a numerical answer of the result of a calculation into the probability of a specific bit string. So that would mean you would have to measure, like you would have to look at the Schrodinger's cat multiple times with multiple cats and calculate what is the probability of seeing the cat alive or dead. Maybe it's 50-50, maybe it's 70-30. And if you know that the answer is the probability that Schrodinger's cat was alive each time, and you see the probability that he was alive each time is 0.536 or something, then that 0.536 is the numerical answer to your problem. So because again, quantum computers can only speak in the language of probabilities. And then finally, and this will be useful for the VQE challenge that we can talk about later, you could measure the average value of a specific magnetic field, like the average value of the magnetic field in the z direction. And the answer could be encoded in that average value of an operator. So I'm going to skip over this. I want to make sure we save enough time here. This is the end. But this last slide is literally my warm-up challenge 2, where it's designed to give you some of those skills that we talked about that you'll need for the NVIDIA challenge on variational quantum eigensolver. So Jackie, appreciate you taking that fire hose there. Happy to answer questions. Let's let Victory come and give his materials. And then I can stay a little late. Jackie, if you've got some more questions, I can answer those.
Yeah, so unfortunately the fire hose is gonna just ramp up after this. Yeah, let me so I'll give a brief just summary of what the supermark challenges are supposed to be. So the supermark challenges are supposed to address the problem of error correction. And the reason why I brought this up is because I've been a participant in hackathons for like a decade now. I used to, just do like classical computing hackathons back in college. And, quantum was like a thing back then, like 5-10 years ago, but quantum's become insanely popular since I was an undergrad. And, the concept of quantum hackathons has come around, and now it's like, these hackathons in Abu Dhabi and, IQ Hack and all these online hackathons and stuff. The one thing that's been missing in hackathons are these types of like quantum error correction specific projects. And just to give a definition of quantum error correction, when existing quantum computers are very noisy. And the way you need to run these protocols on these noisy devices to make them less susceptible to noise, which makes your computation more reliable. So the reason why this hasn't been a focus on hackathons and also just quantum industry in general is because people used to believe that you will get practical applications without error correction. But over the past year or so, the tide has changed where the mainstream belief now is that we're not going to get commercial applications of quantum computers without error correction. So a lot of interest has been coming being applied to the field recently because of this new change in opinions in the field. So
just to chime in real quick, because I haven't talked to Jackie about noise before.
Yeah.
Noises can be pretty intuitive process. Just imagine you're trying to build a computer with like electrons or individual atoms. The only way to get those things to behave is if you make them very cold and keep them very still. You don't let them interact with anything else so that they can exist in their special quantum states. The challenge is that you also need them to be able to interact with you as the computer operator and with the neighboring qubits. And so you have this trade-off where you could take a single atom and make it perfectly isolated and it would be great. It would have no noise, but then it wouldn't be able to talk to anything. And so as soon as you give these quantum states or these atoms, electrons, whatever you're building your computer out of, as soon as you have them interacting with any kind of environment, you could have them interact in a way you didn't expect, and that manifests itself as a computational step you didn't mean to happen. And then imagine those building through every single component of the system, many, many steps along the line, and then you worry that your program is just going to turn to mush because the noise runs rampant and ruins your calculation.
Yeah, thanks for giving more context. And please, I'm haven't really explained this stuff to your first or second year, so please interrupt me when I say a definition that hasn't been defined yet.
Yeah, no, you're doing great, Victory, and teaching. Jackie is a trooper. Jackie and the rest of her team are quite courageous in my view. Like, I didn't start seeing this stuff that they're going to be trying in the hackathon challenge until grad school. And it's part of my role to make this stuff as accessible as possible. And I think it presents, a really novel challenge. How can we take these core concepts like error correction and the NVIDIA challenges on quantum machine learning and make them doable for students who have just started learning Python or just starting taking calculus. I believe it's possible, but the pedagogical and the educational approaches need to be developed and refined. So yeah.
Okay. Yeah. So yeah, exactly. So yeah. So we want to build a computer and it has noise, and the reason why this is not a problem for your phone or this laptop or just classical computers is because the laws of quantum mechanics behave differently, which has been well explained by certain measurements change the state, and also the no cloning theorem. Have we talked about the no cloning theorem yet? Or
we have not.
Okay, so the no cloning theorem just says that if I give you a state and you don't know what it is, you can't make a perfect copy of it.
So there's no copy paste on a quantum computer.
Yeah. So the way that your phone, your laptop, your PS5 deals with errors is it just takes your bit and it just copies it multiple times. So if there's an error on one, it does a majority vote. It just checks for the most popular bit, and then it's one actual, they're called error correcting code. So one error correcting code would be a bit flip code where you take 3 bits and then you use that to encode one logical bit. So those 3 bits, so there's a concept of physical bits, which are your actual bits, and then there's a logical bit, which is those 3 bits represent the logical bit. So I can say if it's all zeros, 3 zeros, that's one logical bit. That's just a logical 0. So if there's an error on one of those bits, and then I check those bits, I can see that, you know, I can have like 0, 1, 0. So then I can say, oh, 2 is more than 1. I know that it has to still be a 0, so an error might have happened. So then I can correct for that error. So I can apply a gate, an operation on that logical bit that corrects for that bit flip error.
It's a pretty, it's not a terribly hard concept. It's like if you've got a walkie-talkie, you say a sentence, but let's say there was static in the middle of the sentence, but the message was clear on either end. So the person is going to say, I didn't get the middle part, repeat. And then you say the exact same message again. Maybe there's static at the beginning, but they already heard the beginning. And then it's clear in the middle. Maybe it's static at the end, but they already heard the end. So they can kind of put those two things together. And the idea of a repetition code is just, you know, the message might be 0, 1, 0, 1. So if you want a repetition code of 5, you take every bit and repeat it 5 times. So you say 0, 0, 0, 0, 0, 0, and send that. And then even if one of those comes in wrong, you, as Victor said, you take a majority vote and you're like, oh, 4 out of 5 of these are a 0. So I'm going to assume they were trying to tell me 0.
Exactly.
Also, Victor, I enabled screen sharing. So if you've got slides or anything, feel free to share those. And also Abby just joined us. Hi, Abby.
Hey, Abby, you want to introduce yourself?
Hi.
How are you? So, let's see here. Can y'all I can share my entire screen. Okay, yeah, I can do that. Okay. Let's see. Okay, can you see this?
I can.
Okay, so basically, I tried making slides, and then I realized I was basically copying this. I can send the link to this reference. This is a quantum computing course that was given by Dave Bacon. He's a software engineer at Google, and this is when he used to teach at University of Washington. But basically, I was basically the general like motivation for all the slides I was creating. I was like, I might as well just share this and then walk through the lecture notes, and that would just be basically give the same concept and also provide more context. And I recommend that you read the lecture notes if you do have the time. But the ones that I think are important for this hackathon is this introduction to error correction, stabilizer quantum error correction, correcting codes, and the false tolerance and computation and the threshold theorem. They're math heavy, but you don't need to really understand like most of it. You just need to understand like the basics, which I'll explain right now. So we'll start with this introduction to error correction, which is lecture note 16 here. And this is what we were basically talking about when we were talking about, you have errors, and this will just tell you what we just explained on how to do classical error correction, where you do a majority vote on the bits that have errors. So then the reason you can't do this quantumly is of the no cloning theorem, which you haven't heard of, but it's quantum. Basically, there's a quantum mechanical law that says you can't copy these states. So then you can't just do whatever you do classically. You have to be more clever. The noise disrupts your state, and quantum noise behaves differently than classical noise. And yeah, you also, what we just talked about, when you measure a quantum system, that disrupts the quantum system. So you can't just measure your qubit and then say, oh, it was like this, and then measure it again, and then say, oh, there's an error has happened. Once you measure it, it disrupts the state. So the way that quantum error correction gets around this is by not measuring the actual qubit, but measuring the parity between states. So by measuring the parity, which is also another word that a technical term, you're basically measuring whether or not an error occurred. You're not finding out which error occurred. And by measuring this parity, it just gives you syndromes, which is symptoms of whether or not an error has happened on your state. Is there any okay, I'll pause there for any questions or clarifications from Joanne.
Yeah, just can you hear me okay? So the parity measurement is just like maybe define that a little bit. My first thought is like it's just checking if two bits are the same.
Ex- yes. So you. Oh no, that's right. That's correct.
Okay.
So then yeah. So you can quantize your classical error correction code. So basically, what this goes through is how to write the classical error code on a classical computer. The M's stand for errors. So if M's
Yeah, so just we've seen those little gates that have the little circle plus through them. Those
yeah.
are our XOR entanglement gates that we saw. So we have at least seen those. And so the M boxes are just saying something happened to the qubit right there, and I'm not sure what it is.
Exactly. And basically based on what we measure, here you apply certain corrections. So I will go way ahead. Okay, so these are the syndrome measurements. So basically, syndromes, again, I said, are just you're using certain qubits to detect whether or not an error happened on your state. So for the repetition code, which we're going through, you have two qubits that you are using to measure the syndromes of your 3-qubit logical qubit, which is what you're running the repetition code on. So if you measure those 2 qubits and you get so these are just eigenvalues, but you can say like +1 is a 1 and -1 is a 0. So if you get a 1 1, then you know that no error happened on your state. So then you don't do anything. If you get 1, sorry, also this is 1 1. Oh, sorry. Okay. This is confusing. I'll say +1 is 0 and -1 is 1. Okay. So if you get 1 1, then you know that an X error happened on your first qubit.
So that would be the X that was what we just covered, Jackie. Abby, you didn't see it. We talked about it in the very first part of the session, but the X is a Pauli X gate. So what this is saying is that so it's like the way I like to give some intuition behind doing these syndrome measurements is it's like you've built yourself a biometric scanning door. It scans someone's thumbprint and decides whether or not they are who you want, who you think they are. And you don't want people to make it through who aren't, part of your organization. So this analogy here is you only want the door to open if the person scans as being part of your organization. So you want some way to detect, is this person or is this quantum state the state that I think it is? So that's what these syndrome measurements are doing. They're a way to detect if an error has occurred, and if so, ideally where it occurred, so you can fix it. So that way it's like you do this whole quantum calculation. At the very end, you get your quantum state, but you don't know whether that state is the state you meant to prepare. So what these are doing is they're giving you a way of saying 0 or 1, yes or no, this is the state I meant to prepare. And it's also giving you a little bit more information. It's saying it's now 2 bits of information that also encodes, yes, there was an error, and I can tell you where it is.
Exactly.
So it's the code helper, right?
Say that again, Abby.
So it's like the code helper to be like, yeah, you have made a mistake. Here you go.
Exactly. That's all. That's what it's entirely what error correction is about, is helping ensure that you're performing the computation you meant to perform.
Yep. Okay, so yeah, so like a supermux circuit like this would be this is all done classically. So you have your logical qubit in your quantum computer, but usually the error correction is done on a classical computer, in a sense of like you measure when you do your measurement, you put your syndromes in like a classical computer and then use a classical program to decide which error correction operation to perform. So for example, if I measured my syndromes and I got these 1 1, oh sorry 0 0, I would know that there's an X error on my top qubit. So then I would apply an X gate on the top qubit. And then that would, X and X are an identity. So the X will cancel out with the X error will cancel out with the X that I applied to cancel it out. That's what the error correction part is.
Because you'll notice, Jackie and Abby, that the X gate uses the identical notation to the bit flip gate. And that's not by accident. The Pauli X is identical to a bit flip. It's just a bit flip being deployed in a quantum context. So that's why Victory was just saying, if you find a bit flip error somewhere, you can you flip it back. You can apply just another bit flip gate on the correct qubit, and that fixes the error that you found.
Yep, exactly. So yeah, that's basically the whole of error correction, actually. It's just you have syndrome qubits that are called ancillas, and then you use those ancillas to measure the parity of your qubits, and then based on the measurements you get, that tells you which error, and then you can apply the appropriate operation to cancel out that error. And these codes are all figured out. So if you know what code you're using, so this is the what is the name of this code, Victory? This one's a bit flip one.
Say again.
Are you asking if it's the bit flip code, or are you asking if it's like a stabilizer code?
Yeah, is it just called bit flip code?
Yeah.
So it detects bit flips. Yeah. So if you know the code that you're using, this table of S1, S2 corresponding to which error, that'll just be in front of you. Like, you don't have to figure that out. All you have to do is set it up so that you can detect, oh, I see a plus plus or a minus minus or a plus minus. And then you just compare that in your table. Oh, that corresponds to a bit flip error on the third qubit. And then you can correct it. So really the skills that you'll need if you were working with a code like this is just the ability to rig up the circuit, like, which is going to be core to basically all of the challenges. Is just using Supermark uses Google's quantum package Circ, which is a Python based thing. They will have some syntax for how do you do a Pauli X gate on which qubit. And then you'll just, code it up in such a way that it detects the syndrome and then implements the correct gate in the correct spot to fix the error. Am I on base there, Victory? Is that kind of what your challenges are about? I was actually hoping you might talk us through a couple of them. Okay,
yeah, sure. I can do that. If I can, did I ever bookmark the?
I can put the link in.
Okay, please do. Thanks.
Also, Jackie, Abby, do you have questions at this juncture while we get the next step set up?
No, I do not.
Okay. And yeah, for both of you, this is advanced stuff. If it's 99% not making sense, don't feel like that's at all on y'all.
And I'll definitely make the notebooks more, I guess. I'll add more meat to it, so it's more of a template, because right now it's very empty. So I'll fill out parts where you don't really need to know to get the general gist of error correction.
Nice. So this is the Supermark challenges file that's in the hackathon repo.
Yep, exactly. So so the goal of the hackathon is actually to create a fault-tolerant quantum computer, which is another term that we haven't defined yet, but it's basically just a quantum computer that runs error correction in a way where the errors don't spread out and just kill your computation. So you can run these error correction protocols, but on quantum memory, so on just qubits that you're not doing computation on. But when you're actually performing gates and doing measurements and preparing states, then you just running error correction is not enough. You actually need to do it you need to run error correction in a certain way where it's fault tolerant.
Fault-tolerant quantum computer is just the ultimate goal of error correction. You've realized a quantum computer that effectively doesn't have any errors anymore because you've corrected them all.
Yeah, and maybe okay. So can you Okay, so this is actually lecture. I'll just say that I'm gonna send these as references, but this is just part of like these last lectures. This is talking through what a fault tolerant competition is and why we care and everything. So anyway, when I go back, so it'll walk you through implementing a STEAM code, which is a certain type of error correcting code. And after you've implemented the basic QBC circuit. So the basic ones are, we just went through the bit flip code. There's the phase code, and after that you can just implement the STEAM code. I think I put the shows code here, but you don't need it. Let me confirm that I put the shows code. So I'm gonna delete this because you don't need this to get your thing done. These two are just to like get the general gist of what error correction is, and then these are not needed for the challenge. So I'll delete both of these so you can just implement the STEAM code. But all these are just quantum error correction codes. Shor's code was the first error correction code that was invented. So in the 90s, after Shor's algorithm, are you all familiar with Shor's algorithm?
We do not know what Shor's algorithm is.
Okay, so Shor's algorithm is why people are interested in quantum computing in the first place. It's a quantum algorithm that factors gets the prime factors of numbers way faster than like a classical computer would.
It's an algorithm whose only application is cyber terrorism.
Yeah.
It's in 1995, Shor's algorithm showed that all of the entire security infrastructure upon which the internet is based could be vulnerable if a large enough quantum computer were built. Which is why governments are putting money into quantum, because they're either worried about someone else getting that capability or they want that capability for themselves. It's Peter Shor also came up with the first example of an error correcting code.
Exactly. And then the reason I added this was because Shor's code is basically a combination of the bit flip and the phase code. But as I said, it's not relevant to the challenge. So I'll remove this. And the reason I added this one is because it's the smallest error correcting. Like, it's been proven that if you want to correct for a single an error on a single logical qubit, the best you can do is five physical qubits. But I just added these because they were in the lecture notes and they were interested, but they're not needed for the challenge. So really, the phase code and the bit code, if you implement those, you can easily implement the STEAM code, because you'll understand like the gist of how to measure stabilizers, which is basically how to measure how to use your ancillas to measure the syndromes of your logical qubit.
So Victory, the bit code in that box is the same as what we just saw in the example you were showing?
Yeah, exactly.
So the bit code is detecting if a bit flip happened. And then phase code, we haven't talked about it too much, but the bit flip code is about detecting if an unexpected Pauli X occurred. And the phase code, I'm guessing, is detecting if an unexpected Pauli Z occurred.
Exactly.
And
then
so
all three of these detect if either a bit error occurred or a phase error occurred.
And Steen does and?
Steen all these three, like Shor's code, 5 qubit code, and Steen code, all three detect both of them, right? It detects whether or not a bit flip occurred or a phase code, and it corrects for both of them.
So then the challenge is the students need to write a program that implements the bit flip and the phase code, and then use those as a subroutine to construct the 5 qubit and the Steen code, or just the Steen code?
You
said you're cutting the Shor code, right?
Yeah. What I was thinking was they would use the phase code and the bit code to construct the Shor's code, because that's how it's done.
Okay.
But that's I now that I think about it, I think I might just like do a whole put like a really quick summary on like just stabilize, like just say like, oh, these are the stabilizers of the Steen code, and then it would just be easy to implement once I give a quick summary of what stabilizer error correction is. Because I think once I just explain like, oh yeah, you're measuring these stabilizers, then you don't really need these two to implement the Steen code.
Great.
And so now that you have an error correcting code that corrects both phase flip and bit flips using the Steam code, then you can make your computer fault tolerant. So to make your computer fault tolerant, you need to basically have we talked about what a universal quantum computer needs, like the gates?
No.
Okay. But we know about gates, right?
We've talked to I mean, I haven't talked about universality, but we've already established a set of gates that gets you there. So we talked about X, Y, and Z rotations by arbitrary angles and the control not gate. And that gets you there.
Oh, perfect. So
like, Jackie and Abby, when we're talking about a universal quantum computer, we're just basically saying, what is the minimum set of basic operations I need to build every possible quantum circuit? Just in the same way we talked about how the control not, the XOR and the AND gate were the basic logic gates that you need for classical computation. The set of quantum gates you need for universal quantum computation are there's a bunch of different ways you could set them up, but the way we've set them up is you need your 3 block sphere rotations, X, Y, and Z rotations by any angle, and then you just need a 2-qubit gate like the control not to make entanglement.
Yeah. I guess with 3 minutes left, I definitely want to do this call again, just to like talk to people through this. So if there's any way we can organize another call similar to this, where I just like walk people through this challenge, and anytime we run into something we haven't defined, we can give a quick summary of it and everything.
Yeah, I think this is good. I actually think, like, in the larger scale of things, it'll be better to set up more regular meetings for everybody, because just, this hackathon was 2 weeks long and this is week 1. Like, time is rather short. I wish there had been a little bit more time, but the calendar of QRX is quite full. But the way I've been kind of hoping to have this set up, Victory, is to have you connected with everybody. Like I'm going to give them your email basically, and then I'm having the hackathon team members pick challenges that they want to work on, and then they have a point person who they can talk to who can help them with those specific challenges. So what I think I'll do at the follow-up for this meeting is I'll send that email. All of you will have Victory's email. You'll have the emails of is Isaac still participating, Jackie and Abby?
I think so. He's been asking me to like meet up so that we can kind of work on it together, but I'm not sure which challenge he's gonna do.
I'll CC him. But so I'll include the students who are still participating, and then in that email we can set up a time if students are trying to tackle the Supermark challenges. We can set up another time early next week to have another meeting like this.
Okay, perfect. Yeah, this is definitely a deep end type thing. So, but if you get this, you'll get this is basically the whole thing.
Yeah,
this is basically what our question is.
Yeah, and again, I've told the students this, like, my only hope for this program is I don't care if a student solves any of the if none of the challenges get solved, I won't be disappointed. The main goal is just to like give students the chance to interact with people like you who are working at quantum companies, giving them the chance to challenge themselves with some interesting problems, and who knows, trying to get students connected to internships at quantum companies is the overarching objective of my program. So having these connections and working on projects like these, I think is really valuable, even if a solution isn't found in the time limit we've set. So both of you talk to and reach out to Victory, and I'll connect you all over email so you can do that.
All right, thank you all. Talk to you all later.
Thank you, Victory.